So today we talk a little bit about how AI is used in software-related tasks. I will present the results of 2 studies, 2 controlled experiments that we run. I will spend more time on the second because for the first one, first of all, it has been already presented in some talks that we had here at USI. And second is published, so you can read more in the paper if you're interested. The second is under review, so it's something new, and I will spend more time on that. Okay. So just to give you a little bit of context, because I know there are some new students. In the past few years, we worked mostly on this project. The goal was to investigate the usage of AI for the automation of code-related tasks like code writing, code review. And this was proposed back in 2018. So the intuition was, we have a lot of data on forges like GitHub, and you can use this data to learn how to automate a certain task, okay? Concrete example, we focused quite a lot on code reviews, okay? And the idea is, you have a lot of code review on GitHub. So you have the code, you have comments written by humans that identify mistakes, quality issues. And the intuition was we could provide to a deep learning model these data, code, comments, and we can teach a deep learning model how to automatically review code, so how to automatically comment on a piece of code. This has been the PhD thesis of Rosalia, and this thing nowadays is basically deployed in industry, okay? The first one probably has been Microsoft, at least the first one who published something about that. And I mean, that work was really an extension of what we did. And now there are more complex AI-based code review tools based on agents, LLM, but this is the basic idea, okay? So we basically moved in a few years from this, like you have the developer looking at the code. Sorry. Okay. To something like this, where you have again the developer, but in this case, it has the help of an agent, of an AI assistant that provides some suggestion on possible quality issues that are in the code to review. Of course, the human is still in control, so it's the human who decides which of the quality issues reported by the AI are real issues or not, and of course, the human can complement on top what is found by the AI. So since we worked quite a lot in this automation, let's say, and since we saw that it has been deployed in industry in many cases, what we wanted to understand was basically what has been the impact of introducing this AI in the code review process. And in particular, what we wanted to do was to investigate these 2 dependent variables, these 2 aspects, like what happens to the review quality, where review quality is basically, do you find the more relevant quality issues in the code that you review? And the time that you spend in the code review, right? This is one of the motivations for introducing AI. Do you save time? Okay. So we decided to run a controlled experiment looking for these 2 things. And we had some very clear hypotheses in our mind that were the review quality will increase, you will find more relevant quality issues, and you will save. Okay, these were our hypotheses. So what we did was to run this study. We asked some developers to perform 2 code review tasks, the 2 treatments, using an AI, not using an AI. Couple of minutes about this treatment. So using an AI really means that they had some code to review. We provided this code to the AI. It was GPT-4. GPT-4 produces a code review. The code review is given as input to the developer, so to the human reviewer. And the human reviewer decides what to do with this input, like consider these suggestions, discard them, add other quality issues on top, so can do whatever they want with this input. Manual code review is the classic inspection, okay, so no support from the AI. These were some numbers. So we had 29 professional developers. We had 12 Python and Java programs. So these were the same 6 programs we translated across the 2 languages. And each of the participants reviewed 2 different programs, okay, in the same language. They could pick if they preferred the Python or Java. But these were 2 different programs, of course, one with the help of the AI, one without the help of the AI. And what we did was to inject the quality issues in these programs. Now you see 48 quality issues. This does not mean 4 quality issues per program, because this would be the result. Because what we did was to inject the quality issue only if it was realistic and if it was difficult to catch. For example, we didn't have quality issues that resulted in the program crashing. Okay, the program was not crashing, was working, so you could run the program. We provided the tests, so we tried to make it as realistic as possible. And also these quality issues that we injected, the type of quality issue was taken from the literature, so these were representative of quality issues usually found in code review. Okay, so we only injected a quality issue when it made sense, and we had from 7 to 3 quality issues per program. It depends. So we collected quite a lot of hours of code review, around 50 hours, and the first thing we did was then to look at the percentage of injected issues that they identified with and without the help of the AI. Okay, this is basically our proxy for the quality of the code review. And with the manual code review, this was around 50%. This is also an interesting number because it supports the idea that these issues were not that trivial to identify. And with the help of the AI, so again, we gave the AI-based code review as a starting point. It was basically the same. Now, you may think that this is due to the fact that the AI-based code review was useless. I mean, if you take an AI-based code review that does not identify any relevant quality issue, you provide it as input to the developer, of course, this will not help, right? And you will end up in a situation like this. But this was not the case because if you take the automatically generated code review as they are, so without any human intervention, they managed to identify around 40% of the quality issues that we injected. So this means that in that treatment, the human was adding 10% on top of what was done by the AI. Okay, I'm simplifying a little bit because these are median values, but you get the point, okay? So there is a difference here in the sense that the human alone was able to find 50%. With the support, they only added 10%. So why is this happening, right? So what we found is that when we provided the AI-based code review to the developers as a starting point, they experienced a sort of tunnel vision effect. So they looked at the comments by the AI. This is an example that I made up, of course. And they focused really on those parts of the code, the parts of the code commented by the AI. But they tended to ignore the other parts of the code where there were other quality issues. Okay, how do we know that? Well, what we did was to take all the code reviews written manually. So among all programs, all the code reviews written manually. And what we did was to count the unique code locations commented at least once. So this means at least one reviewer commented the given line of code. Okay. And overall, across all 12 programs, there were around 500 different lines of code commented by at least one reviewer. Okay. If you do the same exercise for the code reviews in the automated code review treatment, there were less than 350 lines of code, different lines of code commented by the reviewers. So they tended to focus much more on the same areas of the code that were those triggered by the AI suggestions. So basically, it didn't really help. What about the time spent reviewing? So manual code review was like, yeah, you see there is in second. But if you look at the automated code review, it was actually longer. So they didn't save time. Why? Because they spent a lot of time reading the suggestions by the AI, going back to the code, check whether the suggestion was good or not. And then they also had to add on top if they wanted, and not all of them did that. And so, of course, this results in the fact that you are not really saving time. Just want to mention that all the findings that you see here hold when you create a regression model, you control for all confounding factors. These things are all confirmed, okay? Now, this is interesting for one reason. First of all, this is not what we expected, fine. But the other thing is that we presented these findings at the workshop we had with Huawei. If you remember, we had this workshop at TUSI a few months ago. And what they said is, you know, maybe this explains why we do not see that the AI helps during the code review, because they introduced the AI in code review, but they didn't see any improvement in time spent or in the quality of the code. And what we recommended, and this is what they said they were going to try, is that you should use the AI as a further check after the manual inspection. So you first do your manual inspection, and then the AI is only a further check to identify additional quality issues. So you don't save time for sure, but you may improve the quality of the system. So this is what you find here in this work. And again, I didn't go into details. I just want to give you a basic idea because you can read much more in this work. Then what we did 1 year later, basically, was based on these findings that for us were kind of unexpected. We performed an additional study looking in this case at code generation, code writing. Okay, so what happens if you write code without the help of the AI? Because what we saw is that in the literature, there are a few studies, but they focus on productivity, which means that you find claims like, if as a developer, you use AI to write your code, then you can manage 30% more pull requests per week, something like this, okay? So it's all about boosting in productivity. So we had this question, whether there is a price to pay for this boosting productivity, in particular, when it comes to code ownership. So what happens if you become faster, but you are not able to argue for your implementation choices? So you don't really understand what you're doing. And this is problematic, especially in the moment you have to maintain the code, or you just have to fix a bug implemented by the AI that, of course, you will not spot if you don't understand the code. So we performed this second study. This is under review now. And the focus for us was really on the interplay between these two. So we didn't really care about does it boost productivity per se, because we know that it will, especially for how we designed the experiment, you will see. But it was really, do we pay a price for that, okay, in terms of code ownership? So what we did in this case, again, we have a controlled experiment, again, 2 treatments, coding with AI support, coding with no AI support. Again, clarification. This means we provided to participants a controlled setting that was a Visual Studio Code connected to our server. Here, they already had Copilot enabled, but they could use whatever AI they wanted, okay? Whatever they wanted, ChatGPT, what they were used to, does not matter. Here, we provided the Visual Studio Code with the Copilot disabled, and they could use whatever they want, but no AI. So they could use Stack Overflow, documentation, but no AI. Okay. And again, we had participants performing 2 different tasks. I will give you details. One with AI support, one with no AI support. And in this case, we had a different population of participants. So in the case of code reviews, of the code review experiment, we only wanted professional developers because you need expertise to do a code review. Okay, it's not something easy. For code writing, we accepted the fact to have different types of subjects, from bachelor students to master students. This means PhD postdocs and professional developers. So in total, there are 69 participants, and this was done across 3 different universities, okay, this work. So again, 69 participants times 2 treatments. So we had a total of 138 coding tasks. And this is the experimental design we applied. It's pretty standard. I will explain in case some of you is not familiar with it. So this means the experiment was run in 2 sessions. Okay, each session in our case was 75 minutes. And participants were split in 4 groups randomly. So if you were in group A, for example, this means during the first 75 minutes, you would perform a certain task, I will explain later, with the help of the AI. Then there was a break, and then 75 minutes, another task different from this one, without the help of the AI, okay? And what you have in these groups are all possible permutations of task treatment. Why? Because in this way you control for tiring effect, the learning effects. Like, for example, if you always have that they don't use AI in the second session, maybe they are less productive because they are more tired, right? So you want to control for these confounding factors. So it's a very standard experimental design. What is this TD and TE that you see here? Okay, so each participant performed one development task, which is what you see here, which means implementing something from scratch, and one evolution task, which means evolving an existing code base. Okay, this is what TD&T means. And what we did, since we have different types of participants, was to define different tasks for each group of participants. So we had in particular one group was bachelor, one was master, and one was researchers plus developers. Okay, so the tasks, the complexity of the tasks was different for these three groups. So we had the simplest tasks for the bachelor students, more complex tasks for researchers and professional developers. Why? Because they had different backgrounds. So to give you one example, I will show you the tasks for the bachelor students. So these were the simplest one. This was the development task. You see a short summary, but they got basically a PDF with all the requirements. It was about developing a command line application in Python to manage a gift wish list, and then there was the list of features that we wanted. Okay, so this is implementing something from scratch. And the evolution task was extending a game that we gave them, the snake game, by adding 4 features: the computation of the score, wraparound behavior, starting page, and the storing of the top 10 scores that were performed on that laptop, basically. So what happened at the end of the experiments was that we had on our servers the code that they implemented, okay, in both sessions. Now, if you remember, first of all, we want to measure productivity. How do we measure productivity? What we did was to define a checklist for each task. This was not visible to participants. This was for us. And the checklist was used to compute a completeness score. So what we did after the experiment was that the 2 of us looked at each implementation. And we said, OK, the logic needed for keeping track of the score has been correctly implemented. We gave 15% in completeness. Okay, so the maximum was 100%. Clear? Okay, so this is our proxy for productivity. Okay, so we know how to compute productivity in some way. Now the difficult part, code ownership, right? So if in an ideal scenario, what you would do is you run the first session of the experiment, so they implement some code, and then you run a technical interview. Right, to say, okay, now you explain me what you did here, how this works, what happens if I change this, what happens if I change that. Of course, you cannot do that because at the end of a session, you have like the largest run, we had 30 participants in class. So you need to run 30 interviews very quickly because they need to perform the second task. So this will never work. And also there is a lot of subjectivity in the sense that it's about the interviewer feeling of how well you are answering. So it's a little bit tricky. So what we did was the following. End of an implementation session, for example, the first session, the participant completes the task. And we provided in the Visual Studio Code installation that we gave them a plugin. They could click a button. And the code that they implemented was sent to GPT via the APIs, GPT-4. And the GPT-4 was prompted to generate technical questions about the code written by the participant. One clarification here, if you remember, we have development and evolution task. In the development task, we sent the whole code to GPT because everything was written by the participant. In the evolution task, we sent the diff, so the changes that they implement. Okay, and you can get questions like, what happens? These are real questions written by GPT. What happens if I remove this test? Which kind of problems in this method could potentially go undetected, for example? This is something that if you didn't implement that method, may be tricky to answer. Then there were other questions that were about pointing to a line of code, like where do you ensure that the study progress is within a valid range before it is assigned to the exam, for example? Or where do you trigger the final data handling routine once the game can no longer proceed? Okay. So they got questions. We asked for 9 questions per task. And then they had 20 minutes to answer the questions. So they got the questions in the IDE. They didn't have to do anything, just click a button and the questions were generated. And they answered the questions in this file. Okay, so at the end on our servers, there were also the questions generated by GPT and the answers provided by participants. So what could happen and what happened was that the GPT also generated questions like, where is the price converted from string to double? Okay. And if you looked at the code, there was something like this. Okay, so let's assume that the participant didn't write this code. This was automatically generated. Still, that question is trivial to answer, right? You can just search for a keyword and you will find exactly the point where the price is converted from string to double. Okay, so even if you didn't write the code, this was trivial to answer. So what we did was, after the experiment, to analyze all the 1,170 questions generated by GPT across all the complete experiment. 2 of us looked at them, and basically we excluded the trivial ones and the ones that were unclear. Overall, these were 120, so around 10% of the generated questions have been excluded, okay, and have not been considered in the data analysis. Okay, so our proxy for code ownership is basically the percentage of technical questions they managed to correctly answer. So now we know how to measure productivity, how to measure code ownership. Let's have a look at the results. Productivity, as I said, this was kind of expected for us, strong increase in productivity. Why? Because the tasks are not that difficult for an AI, okay? So it can provide good support. But again, this didn't matter for us. What we want to see is if you pay a price right after. So just to show you, this is productivity. So this is the completeness. This is when you put all participants together with AI, no AI. So easy to see, okay? They implement much more in the given time, expected. And the trend is the same, bachelor, with AI, no AI, master, researchers, developers. So no surprise, they also save time, okay. And again, if you create regression models with all confounding factors, blah, 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 this is statistically significant. Let's go to the interesting part, that is code ownership, okay? So what you see here is the percentage of correct answers with AI. So when they implemented with the support of the AI, no AI. And you can see that there is a drop in the sense that when they manually wrote the code, the median of correctly answered questions is 100%. So in most of cases, they managed to answer all the questions correctly. When they used the AI, it was around, I think, 85, 83%, something like this. Okay, so there was a drop. The drop was not consistent across all populations, but I'll be back to this point at the end, okay, because there is something interesting. I mean, the trend is always there, but the magnitude is very different. And this is the time that they spent answering the questions. Usually they spent more time when they use the AI, but when you create regression models, this is not significant. This is significant. Okay, so there is a drop in the percentage of correctly answered questions. When you control for everything, the time that they spent is not really significant. So that thing is not really important. What we also did was, assessing code ownership is kind of difficult. So we also tried to look at other signals in the data. And one interesting point was this. We used TACO to monitor what the participants were doing during the experiment, okay, in the IDE. And something that we looked at was while they were answering the questions, so during those 20 minutes, how many times they went back and forth between the file containing the questions and the source code. So the assumption is if you go back and forth a lot of times, is because you have to go back to the code several times because you don't have a lot of code ownership. If you go less times, it means you know very well how you implemented the code, so you don't need to go there. And what happened is when they used the AI, they went back and forth 87 times on average. When they wrote manually, it was 34. So again, this is another data point that tells you that there is something there. And the last thing I want to show you is this. So now I put close to each other the two main variables that we measure, like the completeness score, so there is no time now, and the percentage of correct answers. Okay, so again, it's productivity and code ownership, our process. And what I want you to see is this result for the master students, where you see that here in terms of productivity, we're the ones having the largest boost by far. Why? Because this experiment, this run of the experiment, was performed in the context of a software testing course in Spain, in a university in Spain. And the task that we gave them, one of the tasks was to write tests. So they were not writing production code, but tests, okay? And the AI was extremely good in that, okay? Like really extremely good. So it gave really a lot of support in that task. So they were the ones who benefited the more from the help of the AI. And they were also the ones paying the highest cost in terms of code ownership. Because if you see the drop of correct answers that they provided, when they wrote the tests manually, it was the median 100%. Again, with the help of the AI, it was around 60%. So they had this huge drop in the median of the correct answers provided. So again, this seems to indicate that the more you benefit from it, the more you pay back in terms of code ownership. Okay, so with that, I will conclude. So I presented you these two works. Okay, the first one is on automated code review, and we try to understand what happens when you use the AI as a starting point for the code review, and we observed this tunnel vision effect. And the second one was about writing code with without the help of the AI, with a focus on what happens to code ownership. So your ability to argue about your implementation choices or to answer code comprehension questions. And again, we observed some relationship between the boost that you get from the AI and the price that you pay in terms of your ability to explain the code.